Okay, our next example is a statics problem in 2 dimensions. This is number 26 from chapter 6 from our applications of Newton's laws. And we have a figure that shows a traffic light hanging from 2 different cables, and the question is, what is the tension in each of the cables? So let's go ahead. Our strategy here is going to be, this is a statics problem. So remember, statics means that the sum of the forces are equal to 0 in all directions. Okay. And we're going to use our free body diagram to figure out what these forces are. And we're going to draw our picture. So our picture, we've got 2 cables hanging down like that, and a third one like that, and then we have a traffic light hanging off of there like that. And we know that the weight of the traffic light is 200 newtons. And the question is, what is T3, what is T1, and what is T2? We also know that this angle is, we'll call this theta 1, and we'll call this theta 2. So there's our picture, and now we can write down what we know. We know the angles, so theta 1 is equal to 41 degrees. Theta 2 is equal to 63 degrees. We know that the weight of the light is 200 newtons. And we want to know T1, T2, and T3. Okay, a couple things to remember about problems like this, statics problems. First of all, the tension is always the same along the entire length of rope. Okay, so any force diagram we draw up here has the tension of 1 and 2. If any force diagram we draw up here, any force diagram we draw down here, we have tension 3, and the tensions are going to be same throughout the entire rope. Okay. So we're going to start by identifying a system to get a handle on these different tensions. The first thing we do is we look at our stoplight. Because if I just identify the stoplight, we know the stoplight isn't moving, and this is a relatively straightforward force body diagram because I just have T1 pointing up, like that, or sorry, T3 pointing up, and I have W pointing down, and they're equal and opposite. And since this is moving, I can completely ignore what's happening up here, and I can just say that T3 is just equal to the weight. So we can go ahead and write down, we just have to worry about the y direction here, so our T3 is just equal to W, which is 200 newtons. All right, we're a third of the way done already, done with that one. Now we're going to change the system we're looking at and move up to figure out what the tension is in these other ropes. And I can do that because I can just look at this point right here and say, well, I just calculated T3 pulling down, and that has to balance T1 and T2 that are pulling up. So let's go ahead and draw our second free body diagram. Our second free body diagram using this now as our system of interest. We have our T2 pointing up that way, T2. We have our T1 pointing up that way, and then we have our T3 pointing down that way. And looking at our angles here, right, that's theta 2, that's theta 1, and that lets us break those triangles up so that we can do some trigonometry on there. Okay, so now we got to break these things up into components and put these things, using Newton's second law, put these things into some form that we can solve for these different variables. So the first thing we want to do is let's go ahead and figure out, it'd be easiest if we could transcribe these angles onto this x-axis here. So let's look at our similar triangles here. Since I've got 2 parallel lines right here, theta 2, this is theta 2 down here, and I have two parallel lines here and here, so that's theta 1 right there. And now I can break these triangles up into components, with the x component being in that direction and the y component being in that direction from these angles here. So let's go ahead and do that. We know that the x component of T1 is going to balance the y component of T2. So again, using Newton's second law, I can write down the sum of the forces. So the x component of T1 is going to be minus, because it's in that direction, T1 cosine theta 1. And then I can see I'm going to add to that T2 cosine theta 2, and that has to be equal to 0. Okay, because we've got this component balancing that component. And now we have the y components here are going to be going up this direction. Now these angles are different, so we're going to get plus T1 cosine, or sorry, sine of theta 1. So plus T1 sine of theta 1 plus T2 sine of theta 2. And then we have minus T3, but we know what T3 is. That's just W. And that has to be equal to 0. Okay, so let me just rewrite those real quick. Solving, bringing one of them to the other side so we can see what this looks like. I've got T1 times cosine of theta 1 is equal to T2 times the cosine of theta 2. That's just bringing one of those over to the other side. And then I also have my other equation, which is T1 sine theta 1 plus T2 sine theta 2, and that's equal to W. So we know what that is there. All right, so if we look at this equation now, that pretty much solves the problem, because we know what T1 is, we know what theta 1 is, we know what T2 is, or sorry, we know what all the angles are, so we know what all of those are. We know what W is. We have two equations and two unknowns. We don't know what T1 is, and we don't know what T2 is. So what's our strategy for solving this one? Well, we can say, we can go ahead and solve for T1 and say T1 is T2 times cosine of theta 2 over cosine of theta 1. And I can plug that into my second equation, so I'm going to get T2 cosine theta 2 over cosine theta 1 times sine of theta 1 plus T2 times sine of theta 2 equals W. Then I can pull out the T2 there, get T2 times the cosine of theta 2 times the cosine of theta 1 times the sine of theta 1 plus the sine of theta 2 equals W. And so then T2 is just equals W is just W divided by cosine of theta 2 times cosine of theta 1 times sine of theta 1 plus sine of theta 2. Which is a little bit of a mess, right? But we know what all of these variables are, and we can go ahead and do this. Now we can go ahead and plug those in and see what they are, but what I'd like to do now is look at the significance of this and see if this equation does what we expect it to do. So let's go back and look at our problem here and ask the question, what would happen if both theta 1 and theta 2 were 90 degrees? In other words, what if you had both of these ropes pulling straight up? And we had the T3 coming down like that. If we did that, we would expect half the weight to be distributed along each of these things. So we're going to go ahead and do that and see what happens. So let's go ahead and plug in 90 degrees for all of these things. If I do that, I'm going to get W cosine 90 over cosine 90 times the sine of 90 plus the sine of 90. And cosines 90 cancel out, so I'm going to get sine of 90 plus sine of 90. Sine of 90 is 1, so 1 plus 1 is 2, and I get W over 2 for the weight on one of those. So that's a good way to check the significance of that. And you can go back and calculate the numerical values for the specific angles that you've got.